So now we'll continue the talk with Aalok Gangopadhyay on experiments with random hives. Yes.
So this is joint work with Hari and Nayanan. So I will be discussing on three things in this talk. And this is the work is experimental in nature. So we have some surfaces which are hard to find theoretically. So we use numerical procedures to obtain an estimate of that and then try to guess or obtain some insight about it. So I'll begin with GUI hives. So we've already seen some of this in the previous talk. I'll quickly go through it. So consider the triangular grid T for a particular value of n. So n is the number of parts in which the one side is divided. And there are three types of rhombi based on their orientation. So these are the coordinates of the general rhombi. So consider a function h from this triangle to R. So we assign real values to each of these coordinates. And this function h is called a hive if for all these rhombuses, this condition is satisfied. So A and C form the long diagonal and B and D form the shorter diagonal. So sum of values on the shorter diagonal should be greater than sum of values on the longer diagonal. So this is a rhombus concavity condition, which we had seen earlier. So now we'll see a Gelfand-Tsetlin pattern. So consider this values, collection of values, lambda j k's. It's said to be a Gelfand-Tsetlin pattern if it satisfies the interlacing condition. So which means that for any entity, this is smaller than the entity to the southwest and it is larger than the entity to the southeast. So I'll describe the minor process. So consider a Hermitian matrix. So we take the eigenvalues of this matrix and sort them in non-increasing order. And then we delete the last column and row. So we obtain the minor and we similarly take the eigenvalues of it and arrange it in non-decreasing order. So we continue this process for all the top minors and we obtain these collection of lambda jks. So these lambda jks form a Gelfand-Tsetlin pattern when we do the minor process. So now I'll show how we get a hive using minor process and large gaps. So imagine we took a Hermitian matrix and obtained its minor process, its eigenvalues using minor process. So we put the values on the sides as follows. The last row is put here, the second last row here, and so on. Now capital lambda, which consists of this sequence, lambda i's, it is said to have large gaps if the following is satisfied. So we take the consecutive difference in capital lambdas, and if the minimum of all those consecutive difference is greater than lambda in minus lambda nn, then we say that lambda has large gaps. So having large gaps ensures that the hive obtained using this satisfies the rhombus concave inequalities. So now I'll explain the double hives.
So not all Hermitian matrices will give rise to like these triangles will satisfy the hive equality.
All will give, all Hermitian matrices with their top minor processes.
But you said that these capital lambda will have to be large enough.
No, that was, so this was Gelfand-Tsetlin pattern.
Correct.
All hives will give, all Hermitian matrix will give rise to a Gelfand-Tsetlin pattern. Here I'm explaining how do we get a hive using a Gelfand-Tsetlin pattern. So we take all the values and we add additional lambda i's. And they are large enough.
The capital lambda is B and R size.
We introduce ourselves. It has to be large enough to satisfy the rhombus concave inequalities.
Oh.
So this is the condition for lambda i's.
So we have artificial generated.
Yes, yes.
And there can be multiple ways to add the capital lambda.
Yes, it just has to be greater than that. So we obtain a hive using a minor process and large gaps. Now similarly, we'll obtain double hives. So in double hive, the rhombus concave inequality need not be satisfied in these four rhombuses on the equator, which crosses the triangle. Otherwise, it's just two hives pasted on one of the sides. So we take a Hermitian matrix X and obtain its minor process, and we paste it from this side. We take another Hermitian matrix Y, take its minor process and paste it from this side. And we take a large gap lambda and introduce on this side. So then we obtain all these values, the two Gelfand-Tsetlin pattern in blue and red, and the large gap in capital lambda. So we assign the value 0 to this vertex, and then for every other vertex, we just follow the arrows and accumulate the values. So we get the double hive.
The top part, we didn't put any large gaps, right?
No, because this value is determined. So for example, if we take here, if we go from this to this, the value would get assigned because of this. It would be the large gap lambda plus something. So now consider this tetrahedron PQRS, it's a tetrahedron grid, so there are points in the inside also. So its general coordinates are given as follows. And these are the coordinates of the vertex. And we have 4 faces on this tetrahedron on which we'll try to associate hives. So these are the 4 faces. The PQS and QRS are the top faces, and there are 2 faces on the bottom of the hive. So we take the double hive in the previous slide and we paste it on the top of the tetrahedron. So this PQS goes on this side and the QRS goes on the other side. And there's a recurrence rule using which we would go taking the values from the top hive, we would propagate it downwards and get the values on the other 2 hives. So I'll explain this rule. So the tetrahedron consists of unit tetrahedra and unit octahedra. So we'll take the unit octahedra and propagate the values downwards, which is as follows. So let's say this is the octahedra and these are the 6 values on the vertices. So the octahedron rule states that the value at the bottom is max of A plus C and B plus D, and from that we subtract E. So this is the octahedron rule. And starting from the top of the tetrahedron, if we go all the way down, we get values at the bottom. And this rule ensures that the values obtained at the bottom is also a double hive. So we take the 2 double hive on the top, we apply octahedron recurrence, and we get the double hive at the bottom. And we will be interested in this hive, in the double hive. So this we have seen in the previous talk. That if we have a matrix X and a matrix Y with its minor process here, then probability that the spectrum of X and Y is gamma is given by this, where B is the Van der Waals determinant and tau is the first 10 numbers arranged in decreasing order. So I'll explain Gaussian unitary ensemble, GUE for short. So first we construct a random matrix as follows. The diagonal entries are real, sampled from normal 0, 1. So this is mean and this is standard deviation. And the complex entries are sampled, the real and imaginary part both are sampled from normal 0 and standard deviation 1 by root 2. Then we obtain this matrix and we take average of matrix M and its conjugate transpose to get the GUE matrix G. And we would also refer to G sigma as a scaled version of this matrix. So we take G sigma X and G sigma Y to be the 2 scaled version of GUEs. So the first step is we sample 2 GUE matrix, then use the minor process to form the double hives, then do octahedron recurrence, and then finally obtain a GUE hive. So this is a process we use for obtaining GUE hives at random. And the probability of getting a hive is connected to the probability distribution we just saw.
What is sigma asking that is it target?
Is it?
Is it target?
Yes, because this rule is bijective, the one we saw. Yeah, this. So if you make this, if you want to go from bottom to top, you just replace F with E. Rest all will remain the same. So given the bottom values, you can arrive at the top values, and given the top value, you can arrive at the bottom value. If you interchange this F and E.
What are sigma x and sigma y?
Some scaling factor, like positive numbers. So we choose it on our own. We want a GV to be scaled by a factor. We call it G sigma x. So using this procedure, we obtain a GV hive. Now we are interested in the expected value of expected surface of a GV hive. So we run this process for a long number of number of times and take the average of them, and we get this surface. So here sigma x and sigma y are both 1, and they are related by the Pythagorean as a Pythagorean circuit. So it's this third side is root 2. We take n equal to 250, and there are 1000 samples we use to average this. Now we are interested, given arbitrary values of sigma x and sigma y, what would be the limiting shape of a GV hive? So for that, we take a degenerate kind of a hive, or a special case of a GV hive, where one of the side is set as 0. So this has sigma 1 and this has sigma 0. So it is a 0 matrix, so all the eigenvalues are 0. And so we get this shape. So we take this shape and form two rotated copies. So here x is equal to 0, and here the third side is equal to 0. And so we define sigma to be the semi-perimeter of this triangle. And we have made a hypothesis where we take these three shapes, we take linear combinations of this to obtain a hive. And we believe that this h, sigma x, sigma y, sigma z is same as the limiting surface for those values.
Is this equality true for all sigma x, sigma y, sigma z, or for large sigma x?
No, that is a hypothesis that is true for all.
This is a working hypothesis, it may not be true. Yeah, it is a working hypothesis.
You know, it is true for certain values.
No, it is most likely never true, but it comes to tell you.
Yeah, so if we look at this is the average estimate obtained using octahedron recurrence. This is what we obtain. This is itself not same as the actual, because the actual one is for limit n tends to infinity and for expectation. So this itself is an estimate of how it should look. And this is how the hypothesis looks for these three values of sigma. And this is the error we have obtained. So it is around 250 here. And this value is around 6000. So it's roughly 4% error. So now I'll move to lozenge tiling. So we have seen this. We take a double hive. We do the octahedron recurrence to get a double hive at the bottom. So if we consider a point inside this, there would be a point on the upper hive. And there is a special hexagon called the excavation hexagon. So what this means is that the hexagon, for all the value at the bottom was obtained using octahedron recurrence. So the octahedron recurrence was, so all the terms on the top panel which contributed to this is part of the excavation hexagon. And these are the coordinates. So if the red point lies in triangle PQR, then these are the coordinates. And if it lies on the other triangle, these are the coordinates. So it's not important to know the coordinates now. So let's take a double hive, and let's take the centermost point as the point of consideration. So the excavation hexagon is as follows. So now lozenge tiling, what we want to do is we want to take a pair of triangles and form a rhombus. So we are interested in all the triangles in this. So we will construct a red graph where the red vertices indicate the blue triangles, and they might form edges if they form a rhombus. So but here we don't allow the two triangles in different heights to form an edge. So we will collapse these vertices on the equator. And then this red indicates a potential matches, two triangles matching to form a rhombus. And with the green one, we indicate the partial edges. So this can't have edges, but we draw this partial edges. So these are the weights defined for the faces. So the hexagons have weight 2, the diamonds in the equator have weight 1, and the partial hexagons have weight 1. So now I'll explain Speyer's maximum weight matching. So the objective is to maximize this dot product, where h is the value of hive at a face. So every red face has a blue vertex as its center. So that is the value of hive at that face. So that is this h of f, and delta of f is defined as follows. It's a weight minus the number of matches. So w are these values assigned to 2, -1, and all those. And this number is the number of matches inside a face. So the objective is to maximize this dot product subject to the following constraints. So each red edge is a value between 0 and 1. 0 indicating there is no match, and 1 indicating there is a match. So we want to find those values x, subject to the constraint that it is non-negative, and any vertex can have at max 1 match. So there are no one vertex can't be connected to 2 vertices. And the interesting thing is the correspondence with octahedron recurrence. This maximum value obtained is the same as the value obtained using octahedron recurrence. So let's say we got this following match. So we bring back the hive. So what this is indicating is this triangle is connected with this triangle. So they form a tile. And if we do it for all of the matchings, we obtain the lozenge tiling. So the coloring rule is defined for the upper and the lower. Green indicates this type of tiling, and the meaning of red and blue gets interchanged from the top to the bottom. So we ran this procedure, Speyer's maximum weight matching for large value of n, and we obtained this. So this is for n equal to 100, where the center vertex is the point of consideration. This is the excavation hexagon, and we can see some interesting properties there. Like there is this frozen region in the of red color here and here, and blue color here and here. So one of the future works like we are interested in is the limiting shape of this height function. So this can look like a staircase where the red is the floor, blue and green are the walls. So from here we can travel downwards. So it is a height function, and we are interested in the limiting shape of this height function. And this is for another point where the excavation hexagon is not symmetric. Any questions so far?
What is the hypothesis?
So here we have prepared a method for obtaining tile. So we don't yet have a hypothesis for this one. So we have made the procedure for obtaining the tilings. Surface tension. So we had seen this triangle hive where we had the 3 types of rhombi, and so we'll have a slack associated with each of this type. So the blue. So I'll explain what the slacks are, but the blue one is called S0, red is called S1, and green is called S2. The hive is essentially this. So we have the rhombus concave inequality. So if it is a hive, then this has to be non-negative. So the difference in the two is the slack. How much? 5. Okay, so this is a periodic hive. So we take a double hive and identify 2 of its edges. So it's like a hive on a surface of a torus. And the surface tension sigma is defined as follows. We take a slack value S as defined in the last slide, and we consider all the periodic hives which is whose slack is bounded by this value S. And then its volume, normalized volume, and the log of that gives us sigma S.
So how do you define like volume?
So it's a volume Lebesgue measure in a high dimensional space, and it's n square minus 1 dimensional.
So you vectorize the height somehow and that forms the body itself. dimensional space.
Or no, like let's consider this is side n, so there are n square vertices, and there's another condition that the average of the value is 0. So the degree of freedom is n square minus 1. So in this dimension space, we define an upper bound on the slack, and the value of the hive should be bounded from.
So basically the entries on the grid points you
Those form that like these all these points form an n square dimension space. In that we have one constraint that summation of all these values equal to 0. That reduces one dimension. So volume of that, so that the slacks are not exceeding a particular value. So I'll quickly go through this. So we have a limit also when one of the slack is very large. I'll quickly skip through this in the interest of time. So we define a rate function, and there are theorem 1 and 2. So we prove these two theorems. And so right now we will be interested in this theorem. What it says is that the surface tension as a function of negative Hessian, the integral of that and the infimum of that equals this value. So the sigma x, sigma y, and sigma nu are the triangles we are obtained. And this denotes the area of the triangle, sigma lambda, sigma mu, and sigma nu. And this V lambda CL is a constant defined previously. So this is in a continuous form. So we kind of consider a discrete approximation of that to obtain the surface tension plot. So the summation over the triangular grid, if we take summation of sigma SV over the triangular grid, we obtain this value. So this is a numerical approximation of that. And we use this equation to form an approximation of the surface tension function. So instead of making it a function of S0, S1, S2, we take this plane S0 plus S1 plus S2 equal to 1, and the slacks being positive. And on this triangle, we would discretize it. And for each point, we would try to find the value of sigma. And the slacks value with respect to a constant has this relation. If we divide it by a constant, then the log s comes outside. So I'll be reading this. So barycentric coordinate is given a point P inside a triangle ABC. Its barycentric coordinates are the ratios of the areas of these three triangles. So we choose a random barycentric coordinate, and we have the three hives we have seen before, and we take a linear combination of these three hives. So we obtain a new hive. So this is a sampling process for obtaining hives for arbitrary values of sigma y, sigma x, and sigma z. So we take a hive and we take a point on that hive, and we consider a hexagon, and we take the average of these slacks inside the hexagon to obtain S0, S1, and S2 for a given point on the hive. And so we obtain these three slacks, and that addition of slacks would be some capital S. So we normalize it and we get a P, and that P would be somewhere on this triangle. So we take the smaller triangle in which it lies, and we compute the barycentric coordinates, which are ABC, and we add these values as the weights. So we take all the points on the hive and we collect all these barycentric coordinates, and the total weights are added. So we have this equation. So if we add up for all the points on the hive, it should be equal to this quantity. So this green dots indicate the weights obtained for each of this point, and these are the unknown values, the surface tension at those points, and that equals to blue, and the blue dot comprises of this constant and this log s factor. Then we take another hive, sample another hive, and we get another one, and we sample lots of hives, the number of hives being twice the number of points in the slack domain. And we also add convexity constraints, because we know that the surface tension is convex. and we obtain this plot for the surface tension. This is the exponential of the negation of the surface tension. So this one is quantitative. And we try to find out the closed form for this surface. This is not the closed form, but it is very close to this surface. And this is the error. So you can see that this reddish color is in the between. So on the interior regions, we get good approximation. And yeah. So to summarize, we found a method, designed a method to obtain GUI hive, and we hypothesized a closed form expression for that. We have a method of obtaining the lozenge selling, and we obtained an approximation of the surface tension. Thank you.
Any doubts?